how'd that do with the conversation?
No.
Oh, we can advertise this again?
Oh, yeah, come on.
For those of you who
All right. We are good to go. And yeah, okay. So, yeah. Anyways, our next speaker, Hongseok. Yes.
Okay, so thank you very much for inviting me for this nice workshop. And so my name is Hongseok, and what I'm going to talk about in the next about 30 or 40 minutes is my joint work with Raphael Monet and Iwai Tae. And I mean, this is more about the inference problem of probabilistic programming language. And actually, my background is programming languages. So what I guess the way you can understand or approach my talk is this non-expert in the inference area, try to explain some inference to perhaps some of the expert. So I hope if I make some mistake, you understand what I'm kind of correct me. And also, if you are like me, you don't understand anything about this area, I mean, it's okay to stop me and ask questions. Okay. So, I mean, I closely work with some of my friends in Oxford, like Frank Wood and Iwai Tae, and they are from the machine learning background, and they're quite interested in probabilistic programming. But when I ask them about what's the main challenge for probabilistic programming, they all say inference. So they really want to have a very efficient inference algorithm. And it turns out coming up with efficient inference algorithm for probabilistic programming is actually quite hard. I mean, there are many reasons about this, and one reason is this inference algorithm has to be generic. It has to, and some people call it universal. It has to work on all kinds of programs that's written in the probabilistic programming language. And what does that mean is some of these algorithms, so like a particular variational inference algorithm, which are quite efficient, they cannot be used because they kind of assume that either like a model is finite, or it can be represented as a finite graph, or sometimes it assumes that some of these particular component of your program, you know how to compute some form of integrations, or how to compute the expectation, and so on. So most of the language, not all, but quite a lot of languages are based on Monte Carlo simulations, because their inference algorithms are based on Monte Carlo simulation. That's because Monte Carlo simulation assumes very little. If you can execute program, or so that you can generate samples. Also, you can score sample. By score, I mean compute potentially unnormalized density for the sample. Then this algorithm works and produce some nice kind of sample if it works. Okay. But meanwhile, in the machine learning community, they, according to what I hear from my friends, they also recognize this designing variational inference algorithm is really hard. So they came up with so-called black box variational inference techniques. So the key idea of this technique is there are some tricky part of the designing variational inference algorithm. You replace it by some kind of Monte Carlo simulation. So in some sense, it makes some idea of Monte Carlo simulation. Also, it makes some idea of variational inference, such a way that in some sense, the user of this technology, or this kind of generated inference algorithm are kind of universal, can be applied to wide class of program. So in fact, this kind of universality is noticed by existing machine learning researchers, and they applied it to probabilistic programs. So for instance, I think Waingate Weber first came up with this, how to do variational inference for probabilistic program. For particular applications, these group of people, and then also some group of people in Oxford, they applied variational inference techniques to, in this group of people's case, they trained topic model for about 200 or 300,000 lines of 200,000 documents, which is quite a big of achievement for applying probabilistic programming language. And in the case of Jan Willems, this second group, they use these variational inference techniques to use probabilistic programming for policy search. So what I and EY started is maybe I mean, this is, in some sense, they took what machine learning people have done, and they just applied it to the probabilistic program. But maybe if we start it a little bit further, maybe we can find some more big, deeper synergy. So maybe these algorithms can be specialized and exploit some of the existing structures of our probabilistic program. In some sense, that's the kind of research direction I'm working on. And if I have time at the end, I will talk a little bit about this a little bit. Okay. So my talk has two objectives. I mean, in England, like every lecturer, when they started it, they learned some form of course on teaching. And the one thing they learn about teaching is that you always have to clarify so-called learning objective in the beginning of your lecture. So I have two objectives in my lecture or in my talk. The objective one is just understand what black box variation inference means, in particular in the context of probabilistic programs. So if you understand this, I'll be really happy and then say my talk is successful. But the second part, at the end, if I have some time, I will explain some of the preliminary results that I'm getting. I mean, this one is all about approximate inference. So the best way to judge it to have some experiments. But I don't have implementation. I don't have experiments. So in some sense, I don't really know whether these ideas are working or not. But anyhow, I thought some of the findings are interesting. So at the end, if I have time, I will mention a little bit about this. Okay, so let me give some other review of a probabilistic programming because I want everybody is on the same page. And also, I want you to have some operational reading about probabilistic program. So here I chose some very kind of contrived example, which is good, mainly good for my talk. Okay, but don't pay kind of too much meaning put too much meaning on this example. So what this example does is that it takes some sample from beta distribution. If you don't know anything about beta distribution, we can just say this is a distribution which returns value between 0 and 1. So you can use it as a probability when you flip a coin. So x randomly initialized to value between 0 and 1. And then we flip a coin based on the sampled value of x. And if the coin flip turn out to be true, then we sample something from sample y from the normal distributions where the mean of the normal distribution has this strange value, x squared. If the coin flip is false, we again sample from the normal distribution, but mean is changed something different. At the end, we say we made an observation. That observation is, this last line is essentially say we observed y modular some noise, small noise, and observed value of y was equal to 3. Okay. Right, that's the reading of the program. One way to understand this program is by actually running it. So let's think about the particular execution. So let's say all the variables are, in this execution, I have two variables, x and y. So these x and y are initialized to 0. And in this particular execution model, or you can say it's an operational semantics, I have an additional variable called w. That track, so the critics say likelihood, like likelihood score, or it track, you can think of it as a weight, or if you are familiar with importance sampling, this w really records the weights in the importance sampling. Now, let's run this program. So we first execute sample, and then we sample the value was 0.8. So then x becomes 0.8. Now we flip a coin. The outcome of the coin flip turned out to be true. Then we go to the true branch. And then from true branch, we use x squared, which is 0.64, as a mean value, and sample it from normal distribution, where 0.64 is a mean value. The outcome was 0.3. That's stored in variable y. And that becomes the result of the if then else. And at the end, we evaluate this normal. So this normal defined probability density, the probability density for normal distribution, whose mean is 0.3, and standard deviation is 1. If you evaluate this PDF with value 3, then that's going to be 0.01 something, which roughly means, this 0.3 is quite different from the observed value 3. So that's why your score is very low. So this is one execution outcome of this execution. So this is one way to understand probabilistic program operationally. It just generates sample. It creates some weight alongside. Okay. And now once we have this sample, then we can do two things in probabilistic program. So if you just ignore this weight, then this trace, the execution trace, the sequence of state you are obtaining is actually a sample from the prior distributions that you are getting from this program. Furthermore, in the presence of probabilistic program, you can actually compute prior density. How you do it? You can see that which random choices are made during this execution. There was first beta, flip, and normal distribution in the true branch. And then you also know which values are sampled at that moment. Just use it and apply this appropriate probability density in those three places. They will allow you to compute this probability density for this trace. To sum up, what I say is you can get a sample from the prior. Also, you can compute probability density of this prior trace. Okay, this is sample. Now, also, this weight directly corresponds to this likelihood score. It means coming from this observation. And this kind of property holds for only all the executions. So there are just some other executions where the first sample was 0.6. Then it happens that it goes to the first branch. We get different value. This time, likelihood score is a bit higher because 3.5 is a lot closer to 3 than 0 point something that we saw before. So then in this case, we again get a sample from the prior, as well as we are able to calculate this prior density. And then there is also likelihood score. So operationally, one way to understand probabilistic program is this generation of the sample to get weighted sample. And so that's an operational semantics, but that's not in some sense what we really want to describe using this probabilistic program. What we want to describe is a posterior. And then there is a standard way to, if you have a way to generate these weighted sample from the prior, then there is a standard way to generate distributions on the posterior distribution via so-called importance sampling. Yes?
No.
Sorry,
Sorry, go ahead.
sorry.
Yeah.
Confusion. Stupid question. How do you get 0.35?
So at this point, the value of y is 3.5.
Okay.
So then I can compute probability density of normal distribution, mean 3.5 and various standard deviation 1. Then I plug in value 3. That will give us 0.35. That's multiplied to 1.
So it's the density of
Yes.
applied to...
Right, density of the observed data.
And should I think of it as how likely it is to be observing free in this particular trace?
Right. That's right. I mean, so this particular, how well it matches with the observation. So it's like a score. If it's high, I'm doing very good. If it's low, then this trace is correct. Now, if you do it, then there is actually this idea of importance sampling can be understood as a standard way of converting this outcome of this operational semantics. In ideal world, you can generate infinitely many samples. You can convert these infinitely many samples into the distribution. So here's a way to do this. So I describe it finite way, but if you send this finite number n to the infinity, you get the distribution. So what you do is, if you keep running the original program, you get weighted sample. You have a trace together with weights and so on. So you have n weighted samples. Then the way to generate distribution is really simple. You just define the discrete distribution on tau where whichever probability mass on tau 1, tau 2 up to tau n. But then now you have to assign probability for each of tau I. Tau I, these probabilities are assigned in proportion to these weights. So that's what this formula is saying. Then you can, I think, maybe Dan knows a lot better than I do. So if you send n to the infinity, I think this converges to this posterior distribution in appropriate sense. Which means like if you want to compute expectations using these samples and then using this actual posterior distribution will give the exactly the same result. Right, so this is a semantic, operational semantics. This is a way to understand how this operational semantics generate posterior distribution. Now the question is, if you just do the importance sampling, sometimes it works really well, but not always. You can kind of see why it doesn't work. When I generate samples, it doesn't have no idea about data at all. It just generates sample according to the, in some sense, script, which is written in my program. Yes?
Sorry, I have another question. So it seems to me that in normal non-programming Bayesian inference, you're not actually finished sorry. Let me rephrase. Sorry. So here the asymptotic result of your probabilistic experiments is a probability on all possible traces of your code,
Yes.
given the data.
Right.
Right.
Then you can project it to the, if you're only interested in the output state, you can project it to the output state as well.
No, okay, but that's not what I'm interested in. I'm interested in going the other way and exploiting this to update my prior. So how do I do this?
So this, I mean, this samples, the infinite amount of sample is in some sense a description of this posterior distribution.
But it's on traces, right? It's not on the actual parameters of my code.
So here, prior itself is also described on the traces. So then everything is on this.
But,
So you can maybe.
I mean, there's a continuous function, ostensibly, from the trace to whatever parameter value you're interested in. And so by weak convergence theory, you'll also get convergence in the law of that particular summary. So this will induce a posterior on every parameter you might be interested in as
okay,
well.
that was my question.
Yeah.
Okay, all right, thank you.
So this one doesn't, I mean, quite often it doesn't work because when you generate trace has no idea about the observed data. So it's in some sense a very unguided way of generating samples. So the many of these idea of the inference algorithm in probabilistic programs are designed in some sense to incorporate this information about the data and then structure of the program and somehow do a little bit more clever, much more clever way to generate samples. So, and then black box variational inference is also another way to incorporate that idea. And that's what I'm going to explain now. So then the idea of variational inference, I mean, it's already explained in one of the talks in the morning. It's quite simple. So you want to, what's my objective? My objective is I want to describe posterior distribution. But it's really hard. So what should I do? So then one approach is you choose family of simple distributions, which you know you can deal with really well. You can generate samples, nice samples really well, or maybe you can compute integration very well. So you have a very simple collection of this family of distribution. Then you change posterior inference problem as an optimization problem. You say, what I want to do is I want to find one of the distribution, one of the theta, which in some sense closest to the posterior distribution as much as possible according to this notion of KA divergence. I'm going to explain what this KA divergence means later. Roughly speaking, it measures how two distributions are similar. So what this one really saying is I want to find closest distribution in this approximating family. Once this is done, and then if somebody asks me questions about posterior, I'm not going to use posterior at all. I'm instead use this approximating, my approximating distribution, and then answer all those questions. Okay, so this is a kind of general scheme of the variational inference. According to what I hear, it's called variational inference because it solves optimization on something like a function-like object. Now the question becomes, then how, the main part of the variational inference becomes this part 2. If you know how to solve this number 2, then you can actually, that's the core idea of various variational inference algorithms. And typically, one of the typical approaches is doing message passing. And you can kind of say, you can kind of imagine what it would look like. You want to optimize this particular objective function. What are you going to do? You just say its derivative is equal to 0. And you want to find an extremer point. If you work out what this equation actually looks like, sometimes you end up with so-called some kind of fixed point equation that can be understood as a message passing algorithm. So that's one way to do it. Or maybe for some simple model, this derivative equal to 0 can also be directly approached for some different means. Now, black box variation, but this requires some understanding about how to deal with this formula symbolically. So black box variational inference take a different approach, which is it try to solve this problem directly by gradient descent. So say some modified version of KA divergence, you take it as an objective function. And you say, okay, what I want to do is I want to minimize that objective function. And then the easiest way is doing hill climbing, kind of not climbing, but going down way. So it does this kind of things based on this gradient. Now, another key idea of black box variational inference is now, this means I should be able to compute gradients. And sometimes computing gradient itself is hard. So you use Monte Carlo estimate of the gradient. So these are the two ideas. Use gradient descent. Second idea is use Monte Carlo estimates of the gradient. Okay, let's kind of work out a little bit on Ka divergence. So here's the definition of Ka divergence. The Ka divergence is an asymmetric way of comparing two distributions. And what it says is it compare so these two guys are probability density function on traces. It compared these two density functions. So you take their ratio. If they are the same, the ratio will be 1. So if you take a logarithm, then it's going to have value 0. If top guy is really high, this value will have value larger than 1. So this logarithm will give a positive value, and so on. So you take a ratio, and then you take average of this ratio. So that's what Ka divergence say. And the reason why it's good to think about this optimization problem is sometimes if you work on optimization problem, you can manipulate, you can get rid of lots of constant in your objective function. That's the case that also happens in this case. So now I unpack this definition. My posterior is the same as prior times likelihood divided by some normalization constant. So this is instance of the Bayes rule. Now the problem, usually difficult quantity to calculate is this normalization constant. So if somebody asks me to calculate this is a really hard problem. But it happens that this Z is a normalization constant which has nothing to do with the theta. And then because of the property of logarithm, I can take it out as a separate sum. And this one has nothing to do with the theta. I can get rid of it in my objective function. So this Ka divergence, one good thing about it is that because I'm solving optimization problem, I can play with my objective function without really changing the solution. So if I play a little bit, then I can get rid of very deep quantity, which is very hard to find. Okay. So then this becomes my new objective function, where now my comparison is between approximating distributions, and then sometimes this is called joint density, like prior density times likelihood score. Okay, so this is the simplification I do. The second key observation of black box variational inference. Now we want to optimize or minimize this function by using gradient. Then there should be a way to compute estimate or should be a way to calculate this gradient. It happens that if you compute this gradient, then you can actually switch, in some sense, this gradient operator and expectation operator. Okay. So my friend told me that, for him, whenever he look at this expectation operator, he always immediately imagine an algorithm. Because expectation operator, one way to read it is getting a sample from this distribution. And then from the sample, you calculate the quantity on the right-hand side and take an average. That gives you a way to estimate this quantity. So if you somehow manipulate the formula such a way that expectation goes outside, that gives a Monte Carlo estimation algorithm of the quantity that you care about. So that's what you can get. And another important point is what I, again, heard from my friend is if you try to compute gradient of estimation, that's really bad. But if you try to compute estimation of gradient, then becomes a lot better. Still, it has a high variance, but it works a lot better. So this is a simple mathematical truth. For mathematical equations, which is true. But this allows you to kind of get much more efficient the algorithm which has less variance.
So I have just a quick question. So you're taking expectations with respect to Q, which isn't the one, you naturally want to take expectations with respect to P.
Right.
So could we say something about how much you lose?
So if you...
I think you do it because it simplifies the math.
That's right. So I think that people do it because it simplifies the math. But if you do it the other way around, it's really hard because that means I need to... So what's nice about this is I can easily generate sample from this approximating distribution. That's why this formula is nice. But if you swap them, I need to generate sample from posterior, which is a hard problem. So what people do is that, they have to use some different techniques. And something that I'm discussing with EY is we are thinking about using so-called cross-entropy method. And So if we have an expectation with respect to the original distributions, then that's very hard to generate. But what we can do is you kind of come up with a proposal distribution, which is good enough to make some little bit of progress, and you keep applying changing your proposal distribution again and again. So there's a cross entropy method. Maybe you know this. So then we are thinking about how apply it to. I mean, for the other situation, we are thinking about apply this cross entropy method to get another approximate algorithm. Right. So this is, just a recap of what I just said. Now, this is a formula, gradient formula that I just showed you in the previous slide, how it converts to an algorithm. The algorithm is really simple. You initialize theta to some initial value. Theta is usually some vector of real numbers. You just initialize to 0 or something. And then you keep applying this again and again until theta doesn't change. And then what you do is that you sample a bunch of traces from the approximating distributions. And based on the sample, you estimate this quantity. And then use that quantity to update your theta. So essentially, you do hill climbing. And this one has, there are all sorts of techniques which improve this kind of simple algorithm. But this is the basic algorithm. Okay, let me show you how this works for probabilistic program. How much time I have?
A little bit more than 5 minutes.
Okay, good. So I'll show you how it works for probabilistic program. So this is a program that you see in the beginning of my talk. Now, how you obtain the approximating family. It's really easy. What you can do is you first get rid of observations. So this observation part is gone in my approximating family. Because I want some of my approximation is one easy way to generate sample from my approximation. And then the second thing I do is whenever I have a distribution, so I essentially maintain the structure of the program, but I just remove the parameters of all the distributions that I use in my program. So beta, instead of using 3 and 2, I use theta 1 and theta 2. Flip, instead of using x, I use theta 3 and so on. And then my question becomes, can I somehow find the appropriate value of theta 1 up to theta 5 such a way that this program, if I just running it, it generates sample which is very close to the posterior distribution.
But, sorry, it looks completely crazy, no? Because you're killing all the control dependencies in the execution of your...
So here the main trick is if I fix particular theta 1 up to theta 5, it's completely crazy. But if I'm allowed to choose right theta 1 up to theta 5, it becomes a lot nicer. You are exactly right. This is a crazy approximation. But good part of this, so some people say, when Jan Willem applied this idea, he doesn't really kill everything. He maintained some part of this, and he killed only some subset. But I just choose this as an illustration.
So you choose theta 1 to theta 5 from a certain distribution, or how do you choose them?
Theta 1, theta 5 are some particular numbers. They are not from distributions. They are numbers which are kind of domain of the optimization. Okay. So now how it works. So initially, we can say the value theta 1, theta 2 are 1. This value is 0.5. Therefore, normal, if the value was 0. Then we run this program. Then that gives this trace. And from this particular trace, what we can do is we can use this trace. Because these two programs have exactly the same control structure, I can imagine this trace actually, reinterpret this trace as a trace of the original program. That allowed me to compute this joint density, the density for the prior, as well as likelihood score. And also, by looking at my approximating program, I can compute the quantity, the density of this trace with respect to approximating program, as well as this derivative. Okay. Then using that, I can update G, and using this compute estimation of the gradient, and using it to update my theta. So, so I put some arbitrary value to show that something happens. Okay.
I think that there are two. I think you're superimposing two completely different things here. Like one is the abstract operation of putting all your thetas and having this isomorphism between traces and computing some kind of metric between the two induced probability distributions on the one hand, which is an abstract mathematical thing which you just explained very well, and the top right little box, which is how you can actually compute a good theta which is going to minimize this KL or whatever metric you find. And this is a completely different question. It's an important question, obviously, but it's a completely different question.
Okay, I thought it should. Okay. Maybe we can talk later. Yeah, thanks.
Yeah, I'm not objecting to what you're saying.
Yes.
It's just a way we
Yes.
can present it in two completely separate
Right.
parts.
So they're applying this the black box variational inference is developed for arbitrary model, and then here I'm just instantiating for. So choosing this particular approximation is arbitrary choice. There needs to be some care about to make sure certain properties are true, but this is arbitrary choice. Then what I've done is also arbitrary kind of decision. So approximation for program is some separate work. Right. So then in the picture, so then what happened is I just generate samples, and then I compute the score. And then based on the score, I compute the gradients, and then you do the gradient descent. Now I think maybe I have 1 or 2 minutes or nothing. Yeah. So for 1 or 2 minutes, I'm going to tell you a little bit about what I've done. So it turns out, this probabilistic program actually a Markov chain. The probabilistic program of my approximating program is a Markov chain, which means probability density, it can be decomposed as density for each step. So then if you exploit that structure, actually this KA divergence has some different form. You can see, the way UI put it is, it just means we are doing lots of integrations analytically. So in the beginning, you do, roughly speaking, a lot less integration. If you do this, it turns out this formula can be expressed as an equivalent formula that does a lot more integration. And then if I can follow exactly the same strategy, that gives a different algorithm. I just show you the picture. That algorithm works in the beginning part is the same. You get generate traces from the approximating program. But the quantity you are computing is not about this step that you are taking. So use this trace as in some sampler for reachable state. And for those reachable state, you are considering all the possible next state, and then do some form of integration there. And that allows you to compute a different way of estimating the gradient. As I said, I don't have an implementation, so I don't know whether it works well or not. But my hope is, because I do a little bit more work in math, I hope it gives a better algorithm. And something similar happens if we do a little bit better. Then there are different algorithms, and that's the only thing that's the whole thing I want to say. Okay, so thank you very much.
Take 1 or 2 questions. I guess sure.
Yes. So the word black box suggests I can take any probabilistic program.
Right.
And I think the part I don't understand is how I generate the variational approximation,
So that part
that is replaced by theta, and how do I, let's suppose a variable refers to, a parse tree. How do I replace that by theta?
Right. So I think I agree with you. So then simple optimization like removing observation is easy, and then now which part to replace theta, that requires another research. So simple heuristic is if I can do it, I replace because these are real value parameters, then just do it. For all the rest, if I can't do it, just leave it there. That also form an approximating family. Whether it's going to give us something good or not, I don't know. But maybe or maybe not. But what Jan Willem did is he just replaced 1 or 2 random choices, remove all the observation, but remove 1 or 2 random choices in the beginning, and that allowed them to calculate the right quantity. So, the kind of policy that they are looking for. But it's a problem, and as I said in the beginning, my background is programming languages. I hope that some idea of program analysis can be used to find a better way or identify more opportunities of these optimization, these approximating family. And for me, that more troubling thing is this black box variational inference, this type of variational inference, the support of approximating distribution should be a subset. And many verification or program analysis techniques, often if you approximate it, they support to become a superset. So that's what bothers me a lot more. So that's why I and UI are talking about this cross-entropy based other approximation technique.
Any more questions? I guess I would agree with, well, I'm not sure if it's agreeing with Stuart, but to follow Stuart's point, I think the problem of defining interesting variational families and ones that aren't so closely tied to the syntax of the original problem is a very difficult one, and it's not really clear that it's a mathematical one. It might be a language design one. How do you give people tools so they can describe variational approximation families and that not be a massive amount of work for them? And also something that composes appropriately. If you take two programs, and you've done the hard work of building variational approximations, you'd like it to be not impossible to combine those variational approximations and so on. Right.
So I have a question, about the relationship between your two talks. You were defining some kind of random walk on the space of traces to sample from the good posterior right. Does that connect in a way?
You can view MCMC as a sequential Monte Carlo algorithm in a much higher dimensional space, and it will produce weights just like Hongseok was using. I'm not aware of how that plays with variational inference.
I mean, your method looks like it's done in a way that respects, maybe it's also closer to what you were programming at the beginning. It's more respectful of the program structure, and yours is more like from the outside. So maybe it's I mean, if your methodology works, maybe it's just shortcutting the.
So in practice, my experience is, this what Dan described in Anglican is called lightweight metropolis hasting. It works really well. It works. I thought it's not very smart algorithm, but somehow surprisingly well. Many examples.
Maybe a last little question. So was there somewhere the idea that you could remember some stuff and not redo your sampling all the time?
So at the moment, because if I do the implementation, I think I will have to think about some memoization. And what I heard for but the kind of algorithm Dan presented, if you start to remember a little bit more, it can save lots of computation. Because it has a lot of computations get repeated. But then we have to find the right balance between tracking extra informations and avoiding some repeated computation. That turned out to be sometimes quite hard. So especially if you try to compile it, so the Anglican compiles program into Java virtual machine, and then run the kind of standard closure runtime system. And if you start to fiddle with it, then you slow down dramatically.
All right. So thank you very much. I'll invite Dana up to